Okay, so the last thing we're going to do to close out this chapter talking about reaction mechanisms is to talk about the arrows that we use in our reaction mechanisms, okay? They have meaning in terms of reversibility or irreversibility. So let's just look at an example here. This double-headed arrow is meant to represent a reversible reaction. I actually draw mine kind of the lazy man's way like that. It's meant to represent a reversible reaction, meaning one that can go back and forth. It's kind of my default go-to for an arrow because in theory, all reactions are reversible. When we use just the single arrow or the single-headed arrow, this is meant to represent a irreversible reaction, one that doesn't go in the reverse direction. And why do I say in theory everything is reversible? Well, it's kind of that argument of, okay, yes, in theory the reverse reaction can occur. You would just have to wait 1,000 years before you would see even one instance of it. And that can very well be true about the kinetics. If that delta G is incredibly negative, then yeah, in theory the products can come together and form the reactants, but it will happen once in 1,000,000 years, right? So we would say that even though in theory it's reversible, it's irreversible, practically speaking. So you kind of can't go wrong drawing these arrows, but we can convey even more information by using these single-headed arrows, right? By showing steps that are reversible and then ones that aren't reversible or that are irreversible. What we're really doing is conveying information about like the likelihood of an event to occur. And so that's what we're going to do, sort of try to be good about when we're doing our reaction mechanisms in the future, is keeping track of steps that are reversible and ones that aren't going to be reversible. Okay, so we're going to just lay down some simple rules for how that could be. Okay, so first of all, being able to spot a reversible reaction arrow. Well, so first, I guess this is an example of a reversible one. And here we have, what does this arrow represent in terms of those 5 categories that we put out? This would be, oops. So this would be nucleophilic attack. So how do I know if a nucleophilic attack is going to be reversible? Well, if my nucleophile is also a good leaving group, then that's going to be a reversible reaction, right? Because the reverse, right? So let's actually color code these things in such a way. This is the forward direction, this arrow. The reverse would be, well, let's do even better about starting at that base, would be the kicking off of that leaving group. So this is, oops. Right, loss of leaving group is one of the other categories. So notice how these are sort of inverse of one another. Nucleophilic attack, the inverse would be the loss of a leaving group. So if your nucleophile is a good leaving group, that's going to be a reversible reaction. Likewise, if your leaving group is a good nucleophile, that's also going to be reversible, right? So if we had started out with just the leaving, started out with what we have drawn on the right, and then switch this around, that would also still be reversible because our leaving group is a good nucleophile. Okay, so that we can spot that by saying, is this nucleophile that's attacking a good leaving group, or is this leaving group a good nucleophile? That's an indication of a reversible reaction. What is it that makes a leaving group a good leaving group? Do you guys remember? Good leaving group equals crappy base. All right, that's the simplest way to think about it. There may be some examples where that's not exactly true, but it's a great way, it's a good first pass. If your leaving group is a good base, it's not going to be a good leaving group. Likewise, if it's a crappy base, it's going to be a good leaving group. So here would be an example of an irreversible nucleophilic attack, right? We still have a nucleophile attacking, what's our carbonyl carbon? An electrophile, yeah. So this is still nucleophilic attack. Notice that there's this resonance type rearrangement that has to take place in order to make it so that that carbon doesn't have more than 8 electrons in its octet. But this guy right here is a ridiculously strong base. So it's going to be a terrible leaving group, right? So this would be an example of a nucleophilic attack that is irreversible. When it comes to pKa value, when it comes to acid-base reactions, that covers leaving groups / nucleophilic attack type steps, right? That's your consideration for those. What about for these proton transfer type steps, right? That was another category of our reaction arrows. Well, for those, we actually have like a quantitative way to deal with these. Remember, how do we tell which direction an acid-base reaction goes in? We look at the pKa of the acid compared to the pKa of the conjugate acid. And which direction does this particular reaction go in? This would go in this forward direction here. Okay, but not only, so that was what we did in our acid-base lecture, chapter, was just sort of determining which directions favored. In your challenge problem, you did go through and quantitate, and what you would have found was, depending on the difference, the magnitude of the difference between those pKa values, that really depends on what your equilibrium value is, how much both of these reactions favor the products. But the large difference compared to these two means that this really favors the products, whereas this is a relatively small difference, so we could say that this is reversible. So the sort of rule of thumb is that if your pKa difference is 10 or more units, it's irreversible. If it's less than 10 units, you'll consider it to be reversible. All right, and then the last category being those rearrangements. These we consider to be irreversible thermodynamically. And why is that? That's because the whole shtick of the carbocation rearrangement is to form that more stable carbocation. So it's not going to want to go back to a secondary carbocation after that nice stable tertiary carbocation is formed. So carbocation rearrangements are just blanket irreversible. Now there's one more last kind of weird category of the irreversible reactions, and that has to do with Le Chatelier's principle. Remember, this is like blast from Gen Chem type of stuff. Remember, Le Chatelier's principle says that you can drive a reaction in one direction or the other by, so for example, I can drive it towards the products by adding more reactant, or I can drive it towards the reactant by adding more product, or I could drive it towards the products by removing products as the reaction goes on. So in this particular case, so first of all, what are going to be my products? We should hopefully be able to tell just by looking at the electron pushing arrows. Here I would have a carbanion in this case. Notice not a carbocation, it's accepting electrons. And nitrogen, N2, right? So why would this reaction be irreversible? Well, because you're going to generate this N2 gas, which is going to quickly leave the reaction vessel. So according to Le Chatelier's principle, you're taking away one of your products, which will drive the reaction even further towards that product side. Not only that, but now the nitrogen's not floating around floating around to be able to collide and actually go in the reverse direction. So anytime one of your products is a gas, that will help to drive the reaction forward. And make that reaction irreversible as well. This is just the last kind of consideration that needs to be made here.